Okay, so I'm supposed to give you an overview of this course as well as overview of each lecture before the lecture begins. So this course is specifically designed to discuss the fundamental background in physical and chemical processes that are used in the treatment of drinking water treatment or drinking water, as well as sometimes for the industrial water treatment as well too. And we'll cover the basis for design of water and wastewater systems, including concepts of disinfection, particle transfer between gas and liquid phases, and particle removal and such. Okay, so that will be what's covered in this course as a whole. In this lecture specifically, we'll start to cover the overview of the water treatment processes and its scheme. We'll also cover some types of reactors that are important in understanding treatment processes and incorporate concept of mass balance to understand these reactor behavior. Today we are going to mainly focus on the reactors that are relevant to our water treatment processes, and to understand them, sort of important concept that we have to apply is this mass balance. So I want to make sure that we are familiar with how to use them. Right, so in the last lecture we started out where why we need water, why we need to treat water, and so on. And today I would like to continue that on, but with a little bit more focus on the water treatment side. So for most of our human use of the water, we get the water in the form that's as clean as possible, right? So we are getting the ones that's oftentimes coming from surface water like lake and river, or groundwater. And its quality obviously depends. So we also talk about very briefly how water quality needs to be suitable for our use, whatever that is. Whether it's for the drinking, industrial use, agriculture, and so on. And to determine that quality, oftentimes we can determine it using either physical, chemical, or biological characteristics, right? And those things will involve some stuff like these things, like pH, temperature, and what kind of particles are in there, clays, some of the chemical precipitates, or microorganisms. And sometimes you may not visibly see them, but they may be still in your water as in a dissolved forms, inorganics or organics. So often some of the examples of inorganic chemicals that are in the water are ammonia, sulfate, calcium, manganese, and so on, right? And I'm sure you can think of a lot more other things. Right. Dissolved organics, same thing. You may have a lot of different organic chemicals that are coming from naturally, or some of them are coming from anthropogenic sources, like volatile organic compounds, oftentimes coming from like a gasoline type of the products, and those things may be introduced into your water too. So for most of our focus, we are going to try to focus them on these two, drinking water and industrial water. Okay, and so we've also covered this in the last lecture too, but basically whenever we have a bunch of these different things that's in the water that influences our water quality, and if we think that they are not suitable for our use, then what we have to do is we have to either remove them from our water, or we have to change their form so that it's not going to influence our water quality, right? And so the concept of the treatment processes that are used in general is that either through this treatment processes we are removing materials, or we are adding some materials, and that might not be a straightforward concept, but when we basically add the materials, that either helps us remove our target materials, or it might change their forms, right? And there are a bunch of these different treatment processes, and I told you we are going to cover all of them over this semester. So don't worry about them too much at this point, but just focus that when we use these treatment processes, these contaminants or these constituents will be removed or changed. Okay, so we also said that in water treatment plants, oftentimes these treatment processes are multiple treatment processes are installed, and they will be used oftentimes in series, as you see here. So water generally flows in this kind of scheme. Okay. And one thing you might notice is that since I'm talking about the water is flowing in this scheme, basically what I can also see is that right now we have multiple processes, right? And I'm just drawing a box here. And each of these things may be corresponding to different processes. And as I told you, it's either removing particles or adding chemicals to change their properties, right? So that means that it's, in a sense, it's reacting with whatever is inside of the water. So in that essence, all of these treatment processes can be considered as reactors. Okay, so then what it means that then these treatment processes are using in a reactor's form, or the other way around, a treatment plant has multiple reactors. Okay, and that's why we are going to focus on this concept of the reactors. And reactors are basically a vessel, a tank or a box where water treatment takes place. And they may be in different forms, right? They may be in the tanks. That's, I think, the most obvious one that we see. But they could also be in something like channels. So water may, travel through in a maze shape, like in a channel. Or they may also be pipes. So right now, I almost highlighted it individually. These things are only reactors. But you see that all these things are connected by pipes, right? And even in the pipes, you see that there are a bunch of other things that are added in as a chemicals and so on. So actually, this itself could also be considered as a reactor because it's a pipe too, right? There could also be other things like filter beds and towers and columns, which most of them look like in this shape, where water either comes in from the up or down, and then there's some kind of packing material, and then water basically passes through them, right? And then some of the water constituents are either removed or added in during that process. So obviously when they're reactor, then their performance and design oftentimes depend on how we design them, right? How we design the reactor. And the reactor type is oftentimes dependent on how the water flows within that reactor, and we'll talk more about that later, and also how fast the kinetics of the reactions for what we are adding or removing. Okay, and obviously if we have fast reactions within the reactor, then the process won't take too long time, right? So a couple examples. Let's start with the kinetics. Fast reactions in reactor. Oftentimes we say something is really fast in reactions when they are considered to be instantaneous, right? The example of this is something like addition of acid or base to the water, right? And most of you are graduate students, so I think when you do experiment and if you need to change pH, for example, then you add acid or base, right? And when you add the acid or base, you just use a stirring bar or something to shake it up, and then you would expect within a few seconds or even within like sub-seconds, the pH will change, right? You don't expect that after you add the base, it's gonna take a minute or even hour for pH to drop fully, right? So that is example of instantaneous or fast reactions, okay? And because of that, oftentimes adding the acid may be done in a setup like here, like so whenever we have a mixer, or it might even be done in a pipe system, right? So actually, if you go back to the treatment process here, and I'm just going to start delete this so it might be easier for us to see. You notice the pH control here is actually with the pipe and not really with the tank type of system. Right, so acid oftentimes completely dissolve, meaning that they they won't be visible. Okay, and goal is to uniformly mix the acid in the water. And oftentimes, because it's such a fast, we don't need a huge size of a reactor to do this, right? Because water can only stay short time before acid completely dissolves in them. And so again, pipe reactor is oftentimes used, and they rely on the turbulence within the pipe to mix the acid. But obviously, there are a bunch of other reactions that takes much longer time, and actually that's the oftentimes the case. So in that sense, the kinetics becomes important. And if that's the case, the size of the reactor oftentimes needs to be calculated to achieve some performance objective. What I mean by that is I'll give you one example. Let's say this is some kind of change or concentration to change, and this is the time. And if you're something like acid, introducing acid, that's gonna just take like really fast thing, right? It only needs short amount of time. Then you won't really worry too much about it, right? You'll just add in how much of the reactor you need to just achieve this. However, let's say if your reaction takes a certain time, like the concentration changes in a relatively long time like this, then you have to decide what target goal you want to achieve, right? If you want to achieve the concentration to drop up to only here, then that's how long it's gonna take in terms of the time, right? Then based on that time, you have to design your reactor in a such way, reactor A, right? If you have different target performance, so if you want to decrease your concentration maybe up to here, then it takes another much longer time, right? And then the reactor has to be designed so that water will stay for that longer amount of time. So you notice that if you want to achieve higher performance target, oftentimes you need larger reactor size. Okay. And here, one of the examples is something like settling tank. So when the particles are in a tank, they may sometimes settle to the ground. That if you want to remove the particles by letting them settle at the bottom, that's one of the example of the reactor that takes longer reactions. Another example is the oxidation of Fe2+. A lot of the chemical reactions takes relatively a long time, and especially the redox reaction takes really long time. Okay, and so if you want to use oxidants like permanganate and chlorine and so on to oxidize ion, it takes a little bit longer time, right? Same thing, pathogen inactivation. If you want to kill the viruses and so on, using the chlorine or other disinfectants, that also takes relatively long reaction time. And if that's the case again, then your reactor has to be designed based on how long it's going to take and what performance you want to aim for. So in terms of understanding reactors, it's always easier to start with ideal cases. And I think most of you, if you have done, if you are from any kind of, engineering background, then you probably have already heard about these reactors. But still, I want to spend some time to make sure that all of us are pretty comfortable with their performance and so on. Okay, so first one that's pretty famous is a batch reactor. Second one is completely mixed continuous flow reactor, CMFR, which just stands for each of the, not this one, this one. Okay, and sometimes people may use CSTR, which is that continuously stirred tank reactor, I think. And then there's a third one called a plug flow reactor. Okay, and we are going to actually try to understand about each of them. So batch reactor, you see that they are in here. Sometimes they're called simply simple batch reactors, SBR, or they might be just called a batch reactor. Either way, it's a batch. And batch means that it's a closed container. Okay, so you don't really see anything going in or anything going out. You don't see them. But in a batch reactor, you have this mixer. So they are completely mixed. Okay, so They're completely mixed. And these things are often used in the lab studies to determine reaction kinetics and what kind of different variables may influence the performance and so on. And in a real system, we may also sometimes design our treatment process based on this batch reactor form. For example, if you have a toxic waste spill or hazardous waste treatment in a ground, so let me say, so this is a ground, and you might have like a contaminants. Then last thing you want is you want to introduce some kind of water flow here, so it's going to go down to the other place, right? So sometimes what they try to do is they might want to contain this hazardous waste spill and then try to treat them within this place, right? So you might add in some kind of chemicals here, and they might be removed in here without adding in water flow, like inflow water flow. Okay, so reaction will only take place in here, and nothing will come. I shouldn't say nothing, but at least the water will not come out and in from that system. Okay, so that's a contained type of system. Some of you may feel like, but how can we really mix them? And that's a good question. There are some people who sort of introduce a ways to mix them together. Anyway, so these things are used, okay? And the characteristic that I want to cover is that because they are well mixed, the concentration here, concentration here, concentration here, and so on, they should all be same, right? Because the tank contents are completely mixed. Okay, so concentration C is uniform throughout the reactor. We don't have, and we assume that there's no density gradient or dead space. So we don't have like a dead space there or there and so on. Okay, and because it's a reactor, if the reaction is occurring, then obviously the concentration should change with time. And I always draw in this way, but some of the reaction may obviously go in the other way around too, right? It might go like this, increases. Reaction occurs over desired time, and again, so whatever you set as the time, and and if you decided this is a time that the reaction will occur, we call that as a residence time. How long the water or reaction will place, and depending on that, your concentration will change to that, right? And here, if we want to understand about these kind of any of the reactions within the reactors, it's to understand them. I think it's important that you understand about this concept of the mass balance. Okay, and here the mass balance is basically almost like a bank account statement. So for one example is that let's say if you have $10 deposit into your bank, and if you have $15 withdrawal from your bank account, then how much do you have? Right, you have plus $10 and then minus $15. So you'll eventually lose, not eventually. So after this, you're basically losing $5 from your original bank, right? And so in that same regard, this change in the mass will be equal to the how much is coming in, how much is coming out. But one thing that's different with the bank is that because we are introducing it as a reactor, so even within that bank account or reactor, the reactions may happen, meaning that the mass might change within there. So we are actually introducing one more concept here, saying that there's some kind of change of the mass due to the reaction within the reactor. Okay, so that's the concept, right? And just that I think up to now this is pretty straightforward. And here, one thing I'm gonna do is that eventually I'm gonna introduce this rate of change of the mass, meaning that all of this thing will be respect to certain amount of time. Okay, but we'll do that later. So for the batch reactor, then the mass balance, we'll start with this one for now. Okay, and then we'll see whether we have any kind of input and output in terms of the mass. And here, let's think about it in terms of this batch concentration here, right? So I'm gonna draw the thing. Okay, and so obviously within here we have some kind of water, right? And in here, let's say we have some kind of dissolved contaminants, A. Okay, so it has concentration of Ca initially. Okay, and we may do this mass balance for any of them, right? We can do them for the water if we want, or we can do them for the dissolved contaminant A as well too. Okay, so here if you look at it, we don't really, and for now, let's try to do this for this dissolved contaminant A. Okay, then we don't see anything coming in or coming out in this reactor because this is a batch reactor, right? Again, this is a closed system. So if that's the case, then we don't have anything that's coming in, we don't have anything that's coming out in terms of that chemical A, so they become 0 and 0. But we might have some kind of reaction that's going on within the reaction, right? So if we summarize this, then basically it becomes delta M equal to delta M reaction, okay? And now for the batch reactor, this is again all in the form of the mass, right? And if you think about it, mass can be expressed as the concentration of that chemical A times the volume of the entire reactor, right? Because the concentration, the way typically we define it is mass over volume. No, I know some of you may feel like, but don't we sometimes use mole per volume? And you're absolutely correct. For this one, let's assume that the concentration is mass per volume. Okay, so M equals CV, and V is constant. This will always be constant for that reactor. So above equation then can be written as, I can basically divide all this thing by volume, and then using that I can make this as delta C equal to delta C reaction. Okay, and now again, as I told you before, what I want to do is I want to make this with respect to time. Okay, so this delta C change in the concentration per time should be same in the both of them, right? So delta C, now I'm just making it in here, and the delta C, I think conceptually you guys know this difference, but I want to just make sure. Delta C is whatever the change that you have, right? So let's say, at T1 and at T2, C1 might be something, CT might be C1 and CT might be C2. Okay, and this C2 minus C1 is delta C, right? But if you do it in this dC dt form, that's infinitesimally small form, right? So we are not making it as T1 and T2 here, but it's very finite form, okay? But either way, I think we can still do it because this concept doesn't change, okay? So dC over dt equal to dC reaction over dt. And the reaction oftentimes from chemistry, again, this is exactly where I'm saying that if you don't have any chemistry background, you'll struggle. And I'm not going to spend time teaching every single chemistry concept, so make sure you are well aware of them. Oftentimes the reaction follows, excuse me, the reaction follows a rate equation. And so this rate can be described as dC over dt, which is oftentimes in the form of minus kcn, and this n can be 0, 1, 2, 3, and so on, right? And then basically this dC dt, it's coming from here, right? Because dC over dt for the entire reactor is equal to the dC of the reaction over dt, right? I can just substitute this to dC over dt here. And assume that we are interested in a concentration change in a reactor from time equals 0 to time equals certain residence time, and where CT equals 0 is C naught. So then that's sort of the integration that we put it in here. Okay, so from here, what I'm going to do is I'm going to do dC equal to minus KCN dt. Okay, and I can do integral in both sides. Okay, and because dC, I'm going to do integral here. dt, I'm going to do integral here, right? And some of you probably noticed that, no, you can't do that because you have to move the variable. Yeah, you are absolutely right. So I'm going to move the variable later too, okay? So anyway, that's how we have the form here. Okay, and then if the n equals 0, I mean from here on now it all just becomes an integration, right? If the n becomes 0, then that this term or this term gets removed. So it becomes just like in the form of this way. Okay, C0 equal 1, right? So then you solve for that, and when you integrate them, it becomes C minus C naught equal to minus K tau. Okay, and then you can put the form in this form. Okay. And if n equal 1, then the expression becomes this. Then you send the C to this side, and then if you integrate dc over c, that's natural log form. So you have this, and you have this. Okay. So I think setting up to here is very important, and I want to make sure that you're comfortable with them. And integration, again, if you don't know how to integrate, then you have to go and relearn them. In our class, we don't do too complex integration. I think the basic thing you probably need to know is like something like this: dc over c becomes natural log when we integrate. That just comes out so often in our environmental engineering designs. So this I think you should know. And it's good if you can actually also know something like DC, C2, DC, C3, and so on. That's all in the same pattern, right? So something like that, I would strongly recommend you go back to your, calculus or integration method to be comfortable with them. But I don't expect you to do every single integration in the world, right? But again, you probably learned it before, so I would. So yeah, I mean, you should know them, right? So in the summary, if I do that for reaction order 0, 1, 2, and nth number, and then we can find the solution for each of them. And then if you actually think about them, please note that the K, the rate constant, obviously will be different depending on what reaction order we have for that certain reaction. Okay. Oftentimes for many of the treatment processes, they follow reaction order 1. Some of them sometimes follow the reaction order 2. I rarely seen anything following more than 3 and so on. Okay. All right, so now I'm going to move on to the next reactor, CMFR, completely mixed continuous flow reactor. Oh, by the way, one thing. So I think one of the beauty of this recorded lecture is that if you think you're losing focus and so on, you can pause it anytime, stretch your body, and come back to it, right? So don't feel like you have to just sit through and keep listening to me. If you think you're losing a focus, do something to refocus, right? I think during the class time it might be a little bit difficult to do that, but recorded lecture, I think that's one of the big advantage that you have. You have the control of when you can play and how you want to pace it. Okay. Anyway, so I'm gonna move on with this completely mixed continuous flow reactor. So now, compared to the batch reactor, the difference that you have is now here we have the inflow of the water and outflow of the water. And this is actually really common for a lot of the water reactors that's used in a water treatment process. Okay, and this is used for something like rapid mix tanks. We talk about them before, when we want to add base or acid into our water. We might use them for some of the activated sludge process, which is a type of the biological treatment reactor. And we may also use them for flocculation tank. Don't worry too much about if you don't really get the idea yet. Okay, it's okay. But anyway, so the basic concept is that there's some kind of inflow of the water which contains that chemical A or whatever chemical. Okay, so Q in is how much water is coming in terms of the flow, and the concentration of that chemical A in that water flow. Okay, and also water is coming out from the reactor as well too with certain concentration. Okay, and within the reactor, it's always completely mixed, so concentration C is uniform. Again, so characteristic is the uniformly mixed and no dead space. The concentration in the reactor is same throughout anywhere, so C1, C2, C3, and so on will be all same, which means that right here, when it right at the edge where it's coming out, it should be same as anywhere else, right? So that means that concentration that's coming out should be same as the concentration within the reactor. Okay, so C reactor. Yeah, I'll just say the C reactor is same as C, should be equal to the C out. Okay, and this is actually really important characteristic of the CMFR. Okay, it sort of influences its performance. Also, whenever you have to use the mass balance equation and so on, this comes out, right? The residence time for this CMFR is not similar to the batch reactor. For the batch reactor, you decide how long you want to let the water stay in that reaction, right? In case of the CMFR, that's not the case. In a CMFR, residence time is that how much water in average stays there, okay? And that can be determined using this V over Q, okay? However, one thing to note is that in this CMFR, not all water will stay for the same time, okay? There's a distribution of the residence time, meaning that, let's say if I have tau and here, this is time variable. And if I see fraction of water, fraction of water, okay? Then you might have something like this. I don't know. It might not be normal distribution like this. But anyway, you may have something like this. And then, so some water may stay for really, really short time. Some water may stay really long time. In an average, it stays over this tau over V over Q. Okay, so that's the characteristic with the CMFR. I'm going to just continue on with the plug flow reactor for now and then come back to the mass balance for both two reactors. But anyway, for the plug flow reactor, which looks like this, and basically here the water just flows in one direction, right? And when the water flows, oftentimes they flow in the same pace. So velocity is same, okay? So some of you may feel like, yeah, that's like a pipe, and you're right. It's a pipe. Sometimes we also say that columns, which you remember like this, may perform a little bit more like a PFR too. Not always, but sometimes. Okay, and here basically why we call it a plug flow reactor is because we can think of the water as a plug here. And it's continuous, so water should fill up all the thing, but just ignore that and just focus on this plug of the water that comes in. Then this plug, after a certain amount of time, moves to here, okay? And after a certain amount of time, it moves to here. And after a certain amount of time, it comes out from the reactor, right? And here, the key assumption that we have is that this water is not really spreading apart, right? This water stays at that plug and moves in that pace. Okay. And so the characteristic then is that it's a constant flow. And because we are assuming that it's moving as a plug, the water is moving as a plug, we won't really have an internal mixing, meaning that the concentration here and concentration here will not be same. Okay. But within that plug, within this plug, the concentration is same. Okay, so again, plug of pieces of water march through reactors. In this case, residence time tau can also be calculated using the volume of this entire reactor. Again, this is not volume of the plug, but volume of the reactor divided by the Q, how much goes in terms of the water and how much goes out. All pieces of the water then have the same tau. So unlike the CMFR reactor, for this one, the fraction is here. All of them will only stay in the reactor for that specific tau time. Okay. Obviously, those three things are called ideal reactors because they are in an ideal form. And in reality, many reactors do not behave ideally. Okay, and some of the reasons may be due to the mixing efficiency. We say it's a completely mixed, right? But we don't really have. If you actually do experiments, you notice that mixing may not always be perfect all the time. So due to the mixing efficiency, you may also have a dead space. You may have sometimes a short circuiting, meaning that really short resonance time due to the poor fluid mechanical design. And also, and due to all of these things, it may behave non-ideally. Okay. Also, this is not really a case of ideal and non-ideal, but in a lot of the reactions that we say, we are sort of ignoring the diffusion and dispersion, right? But for example, like plug flow reactor, we are saying that that water plug is moving as a plug, right? And it's not spreading. But you know that that's not really the case, right? If you put a water on your desk or something without any container, you know that it slowly spreads out, right? So that's a dispersion and diffusion that's playing a role. Same thing, any chemical that you have within the reactor should have a natural tendency due to the energy thermodynamics. It should diffuse, right? So all those things, when we include them, they might not necessarily all the times behave like an ideal reactor. But we will come back to these sort of the characteristics of non-ideal and maybe also diffusion and dispersion later, right? But not today. Right, so, but I want to just introduce this mass transport mechanism just for the sake of it, okay? So mass transport deals with the transfer of the mass from one point in the system to another, and there are three basic mechanisms: advection, molecular diffusion, also known as Brownian diffusion, and dispersion, okay? And again, for the ideal flow, only the advection is considered, okay? Advection is basically that when you have water, so let me explain it this way. So if I have a pipe, water chunk moves, right? And then let's say the chemical A is also in part of here, okay? Then if that water chunks move in the same pace and the chemical A moves along with them in the same way, so they just kind of stay in that chunk of the water and just move around, that's advection, right? So it's just following the movement of the water together. Molecular diffusion is that if you let this A stay here, it might want to just like spread apart, right? It doesn't want to focus in here, especially if you have nothing else. So surrounding the water chunk, there are other water, and let's say if these things do not have concentration A, they want to sort of spread apart, right? So that's called a molecular diffusion. Dispersion could also occur that as you move the water through here, there may be a turbulence, right? Turbulence creates the sort of a difference in the velocity and so on. And those things may also help the chemical A to spread apart and change in its concentration, right? So, but again, for the ideal flow, PFR, for example, PFR, we only consider that advection is there, okay? And we will come back to diffusion, dispersion later, but for now, just advection, okay? So again, for the advection, within that chunk, we have no spreading of the C, and we have uniform velocity profile. And if that's the case, let's start with the CSTR, okay, or CMFR. Okay. Again, what's coming in, that's advective flow. It's a QC0. Okay. So in here, I put it as Q in and C in, but C in is the initial concentration. So whenever I have initial concentration, I tend to use this 0 as a script. Okay. Because it sort of signifies for T equals 0. Okay. But we'll come back to that later. Okay, and also if we don't want to change the volume of the reactor or volume of the water that's within the reactor, then we also have to keep how much water we put it into the water same as how much of the water we put out from the water, right? So Q in and Q out are oftentimes same in many of the reactors that we see, and therefore we just simplify them as a Q without any subscript. So that's sort of where this QC0 comes from, okay? And what's coming out from the outflow will be just QC, right? And this C here, again, is the concentration within the reactor, and that's, for the CMFR reactor, we said that's same with the C out, right? And therefore, we have the QC here, okay? All right, and also just concept-wise, QC, right? Q is the flow of the water, so that's volume per time, right? And concentration is mass per volume, right? So if you multiply them together, then it basically becomes the mass per time, right? So how much of the chemical A is, moving or changing with respect to the time. Okay, so that's sort of what this product QC signifies. In case of the defective mass transport in PFR, the same thing. There will be QC flowing in, right? Q in, C in, and so on. And for the PFR, Q is actually velocity times the cross-sectional area. So this is a cross-sectional area. And then how much it's flowing is the velocity. Okay. So we can also oftentimes describe it with VAC as a QC. Okay. And sometimes because A is constant, we may express them as MT, which is same thing as QC, over A. Okay. All right, so mass transport in a plug flow reactor, you need to tie together with the reactor hydraulics and reaction kinetics. So basically what we are going to do is we're going to just try to focus on the plug of the water. Okay, so not for the entire volume, but for that plug of the water. Okay, then the concentration C is there, and then because there must be some kind of reaction going on within the reactor, it might change its concentration by some degree, right? So that's where this delta C comes in. Okay, and for this plug up the water, I'm just going to say that has certain kind of the depths to it, so I'm going to introduce it as a delta X. Okay, and so as the water travels here, the time passes, right? And as the time passes, the water chunk moves from here to here to here, right? So the distance gets far. So you can say this as a time of the travel, time of travel, but you can also say this as a distance because Vt will basically be equal to d, or distance x, right? So in that sense, then we see that the concentration decreases on and on and on, and that can be described as this delta C over delta X, okay, which will basically be C1 minus C2, X1 minus X2. All right, so here, again, just remember this characteristic that we talked about before, and now I'm going to introduce this kinetic rate concept because I want to use all this thing into the mass balance of the PFR, okay? So now, again, focusing on that one segment in the PFR. One segment meaning that this, okay? Then the delta M equal to M in minus M out plus minus delta M reaction. So that's the same thing that we use. Then V delta C over delta T. So this is basically this thing, okay? And then M in, so this I'm gonna now express that all in terms of this, okay? Just make sure that I'm not confusing you too much. I mean, this is kind of really weird way of saying it, but basically just assuming that everything is in now with respect to the time, okay? So if that's the case, now we can put them in here. The volume And again, the volume here is not the volume of the entire reactor, but it's the volume of just this chunk. Okay. Okay, volume delta C over delta T, and M in is QC, right? And then M out is QC plus delta C, because this is basically how much mass is coming in. This is how much mass is coming out from that chunk of water. Right? And then the reaction will be the KCN, but now we have to put it in respect to the M, so we also have to add the volume. Right? And take out all the common terms and so on. So QC here and minus QC here, so those things can be eliminated. Okay. Okay, so then it becomes minus Q delta C as shown here, minus BKC in there, B delta C over T is there, right? I'm going to divide both sides by the volume. Okay, and then you see that this gets eliminated, so you will get delta C over delta T equal to minus Q over V delta C minus KCN. Okay, and again, remember that the V here is only for the one segment. So if you actually go back to this, and if you look at it, you guys remember that we used that cross-sectional area A, right? So the volume here that we want to describe is the area times the delta X, right? So that's how we are adding in there. So now I'm changing this volume to that form, delta X over A, okay? And then since this is delta X2, now I can put delta C over delta T equal to minus Q over A, delta C over delta X minus KCN, okay? And now, again, the delta is for whatever the certain amount of the difference. Now I'm going to make that into the infinitesimally small fraction. So make it into the partial differential equation of dC over dt equal to minus QA, dC over dx minus KCN. Okay, so that's sort of the final form of the PFR. Okay, dC over dt equal to minus Q over A dC dx minus KCN. This equation basically describes the C as both a function of the time and distance and reaction rates. Again, this is again for the ideal case, PFR, where only the vector mass transport is considered. I think some of you, if you have taken some kind of hydraulic concept, then you guys probably have already learned about this before. But I know some of you haven't. So make sure you are comfortable up to here. Okay, follow through the things. Make sure you understand how I'm doing it. And if you are not, make sure you try to grasp that. Okay, you are more than welcome to ask me a question too. So now here, if I need to integrate this, that's going to be way too much of a hassle. But to save you, we have this concept called the steady state performance. Okay, and from a process point of view, we design and operate often at a condition called a steady state. Okay, and steady state is a condition where the concentration at distance x is not changing with time. And what I mean by that is, let's say if I have this pipe reactor, and if I focus on the concentration in each of different places, x equals 0, x equals A, and x equals L, and they might change like this. And you guys remember that if I have done a distance, okay, and then a concentration, and it was in the previous slide, then you guys sort of remember that we had something like this, right? So here, this is where x equals 0, this is where x equals A, this is where x equals L, okay? And in that sense, then, I mean, that's basically what we see here. But if it's non-steady state, sometimes what happens is that this concentration here might change, right? So if I focus on at x equals A, and after reaction starts for a certain time, what you might actually start seeing is that you might see something like this. Oh, sorry. Okay, so here you might have initial hiccup time of like I don't know what's happening, but it needs some time for adjustment. And after that, it just starts performing in the way that it's designed to be. Okay, and we call this, when the concentration doesn't change anymore, as a steady state. Okay, and we call this place where the concentration might change due to whatever the reason is, as a non-steady state. Okay, and this is actually lifesaver, because this means that at steady state the concentration doesn't change with respect to the operation time. So that means it's a dc dt equal to 0, right? Because the concentration doesn't change with respect to the time. Okay. So then, as I told you, we are saying that, oftentimes from process view, we design and operate at steady state. That means that at steady state, dc over dt equal to 0 at steady state. So we can actually make this thing become 0. Okay. So then, it's just playing around with the equation, and you can always put this q over a is again the velocity, right? So velocity dc over dx equal minus kcn. And now you feel like, yeah, it's kind of doable. Now I know dc and cn and dx. It's kind of similar to the batch reactor integration that I've seen before, right? So again, if n equals 0, you have this, and then here, just one thing, the integration is now different, a little bit different, because instead of time for the batch reaction, now we have this distance, right? So x equals 0 and x equal L. So what we are doing is that now for the pipe or the plug for reactor, this is where x equals 0. This is where x equal L when the length is L, right? So when we have that, then we can integrate them and get it in the form of this. Okay, C minus C naught equal to minus 1 V over KL. And it becomes C minus C naught equal to minus K L over V. Okay, the length of the plug for pipe or plug for reactor, divided by the velocity. And remember that the tau is basically volume over Q, which if you divide both of them, volume by A, that becomes L. So this is the volume, okay, and this, whatever, is the cross-section area. So V over A equal L, Q over A was velocity. So same thing, right? So L over B basically becomes a tau. So then this also becomes C equals C naught minus KT. Okay, and by the way, I don't know why I made this in a capital way. It's the same K with the reaction rate constant. Okay, so that's sort of what you typically see if the n equals 0, right, for the reaction. Okay, if I want to re-express this in a form of the fraction remaining, I can do so too. So if I rearrange them, I can put them in this form. C over C naught equal to 1 minus K over C naught tau PFR. This is sometimes powerful if you want to calculate with respect to a certain amount of the time, how much concentration will be remaining with respect to initial concentration. Or you can do it in the other way around, which is oftentimes more useful, is the tau of PFR. So if I want to achieve certain amount of the performance goal, how long the water needs to stay there, and so on, right? So you can do the same thing for the reaction order of the 1 and 2 too, and resolve them, okay? And I will actually leave that to you, okay? So you can do it on your own time to make sure you do it. And then you can, get the solution for C over C naught and tau PFR by just rearranging them too. All right, so now we are going to do the same thing for the CSTR or CMFR. And for the CMFR, it's actually much easier. So again, the characteristic is that, the C in is there, Q in is there, Q out is there, C out is there. Again, Q in and Q out has to be same, Q, and the concentration within the reactor should be same as the C out. Okay. So now, same thing using the mass balance equation. Delta M becomes this. Okay. M in is Q over C naught. So that's what we get from here. Okay. And then M out is QC. Okay. The reason why it's not C out is again because it's basically same as the concentration in the reactor. Right? And then the reaction is BKCN. Again, if you're interested in the steady state, then delta C over delta T becomes 0. So we plug that in here. Then QC naught over minus QC minus BKCN is there. Divide everything by Q. Then it becomes C naught minus C minus, I think originally it was B over Q, KCN. But B over Q is tau, right? Tau. So that's how we convert it here. Okay. So that's what we get for the solution. Yep. Yeah, I think this is typo. Sorry. C M F R. Okay, mass balance with CMFR steady state. So then using this, you can just plug everything in. N equals 0, then basically becomes this. We can also re-express them in the form of the fraction remaining or the tau retention time. Okay. And we have the same thing, reaction order 0, 1, and 2. Now, I'm just going to do just comparison of this thing real quick. So between PFR and CSTR, we were able to solve for them in terms of the concentration and exit. We were also able to compare them in terms of the performance, how much is remaining, and tau PFR as well too. So using this then, we can actually try to compare, right? If I want to achieve same goal, like whether it's I want to remove 99% removable or 99.99% removable, I can oftentimes achieve them using both either PFR or CSTR reactors. And then they then can be compared using something like tau, PFR, and so on, right? So that's what I want to do here, okay? So compare the reactor size of the CSTR relative to the PFR. And if n equals 0, then I'm just going to use this information here. Oops. Okay, and then if they are 0, then they are same, right? Basically, they have the same equation here, so they are same. Okay, if n equal 1, again, I'm just going to use these information there. Okay, and they're expressed in this way. If I just remove the same terms, it becomes this. Okay, and remember that T equal Q over B. So for the same flow rate, if we design for the same flow rate of the water that we want to treat, then basically the tau of CSTR over tau of PFR, that ratio is basically same as the volume of the reactor of the CSTR over the volume of the PFR, right? So now I can also make this as B over CSTR over V of PFR. Okay. And now that means that compare the reactor size of the CSTR relative to the PFR. So if it's n equal 1, then we are still using this information. Okay. And now I'm just going to plug it in a bunch of different things. So if I want to have efficiency of 80%, that means I want to remove 80% of the concentration. So at the end of the reactor, I only have 0.2 of the initial concentration, right? And at the 90%, it's going to be 0.1, 95% 0.05, 99% 0.01, and so on, right? I can, this C naught over C is just the inverse of that. So, if you flip it, it just becomes like that, right? And then when you have all these numbers, you can just plug that into here and find out the ratio, okay? So for the efficiency of 80% at n equal 1, we see that the T CST over T PFR becomes 2.49, okay? And I told you that's same as, right? So that means that to achieve same performance goal, you need 2.5 times larger CSTR than if you were to do it with the PFR. Okay. Now, if you up it to 90% removal efficiency, that ratio becomes even more bigger. So it originally was 2.5 for 80%, but now it's 3.91 for the 90%. Okay, so that's what we see here. And in the summary of the table, 80%, 90%, 95%, 99%, n equals 0, and it's 1, 1, 1, 1. So if the reaction rate order constant is 0, it doesn't matter whether we use CSTR or PFR. But if it's n equal 1, then you see that always the CSTR requires much more volume of the reactor than PFR. When n equals 2, that difference becomes even more significant, right? So in all cases, the tau CSTR is always larger than or equal to TPFR. And for high efficiency, this ratio also increases. And therefore, for the many water treatment processes, we prefer PFR because it will require smaller footprint or smaller volume of the reactor compared to CSTR. However, it does not mean that we always build PFR. We sometimes also use CSTR for intentional mixing, like rapid mix tanks and so on too. Okay, but you guys now know sort of the performance difference. And if you want to think about why that might be the case, just think about it, right? And I might give you the solution later, but I want you to think about it too, right? So now you know the characteristic of these two reactors, right? CSTR and PFR, right? So using this, just think why CMFR seems to be less efficient than the PFR. All right, so that's all for today's lecture, and we will continue on with this concept of reactor. So, and this concept of the reactor and mass balance will always come up from now on in this semester. So make sure you're comfortable with all of this concept. All right, so with that, thank you very much, and I'll see you in the next lecture. Bye.